why is this happening? Of course we can find mathematical proofs, but they are kind of long and not very enlightening. On the other hand, if we use mechanics, this thing is obvious. And you can make so many exercises on the basis of the notion of a gravity center that I believe that your kids in math circle at home will enjoy them very much. And so I said it already. This is related to a gravity center of a rigid body in mechanics. Now, if you want to entertain middle schoolers, then your instruments, mathematical instruments, will be restricted. And to give arguments that those things really happen, you have to put under the carpet some things and build up a little bit of physics intuition in the kids. And this is what I try to show to the participants on Saturday in the fair. So now, there are simple experiments which can be done in classroom, showing that, for example, if you have two balls connected with a kind of stick, but the stick shouldn't be very heavy, because you have to have control on the weights. And if the stick is heavy, you don't know what will happen. But let's pretend that the stick is very, very, very light, and all the heaviness comes from the bodies, from the balls. Okay. So, mechanically speaking, this is a rigid body. Why? Because it's impossible to deform it. It's a rigid body. And this rigid body, mechanically, has a gravity center. Now, here is where the experiment enters the picture. How to find the gravity center of this body. Then playing a little bit with the balls and the sticks. If the weight here is, well, the mass is m1, and there the mass is m2, of course these are positive masses. Then the gravity center will be somewhere on the stick. And we can even find almost precisely where this will be. The thing is that if we call this A1, A2, and G naturally, then this G is fixed by the relation that what?
AG over G, D.
Okay. A1G over A2G is
M2 over M1.
Yes. And it's a standard rule in mechanics that if you have the weight multiplied by this segment, it has to be the same as that weight multiplied by that segment in order our solid to be in equilibrium. Otherwise, it will be moving in different directions. All right, so this is the first thing that you do. For example, if M1 and M2 are equal, then the gravity center of this system will be the midpoint. Then, what will happen if we have three balls forming a triangle, because it has to be a rigid thing? Well, here you can show, by using experiments, nothing more, that actually when you make this triangle physical, and when you suspend the triangle at one of the vertices, then we know there is a gravity center of this body, right? And if you consider the vertical line starting at that point, then you immediately realize that if the gravity center is off this line, the triangle will be swinging. Everybody knows that. So that if the triangle is in equilibrium, the gravity center will be on this vertical line. Right? Then the other thing is that what we can observe is that this point of intersection is exactly the gravity center of the stick with two balls on it. So how to explain this? I don't know. This is experiment. You just observe it. You see the nature never goes wrong. So you have this. There is the gravity center of the triangle, and this vertical line will pass through the gravity center of the stick. Okay, now you can do this for all the three vertices of the triangle. Suspend the triangle, do the things, and you see that the corresponding vertical line will be passing through the gravity center of the triangle and the gravity center of the opposite stick, the opposite side. Right? Okay, now let's go back to Archimedes and prove that indeed the three medians intersect in one point. Make the triangle have three equal masses. Then this vertical line passing through the gravity center will be passing through the gravity center of the triangle will passing through the gravity center of the segment, which is the midpoint. So that this vertical line is a median. When you do these things two more times, you will see that the other two medians will have to pass through the same point, the gravity center, because that's that. This is what is happening. Right? Now, there is an addendum to this property that actually this common point divides the medians in ratios 2 to 1 counted from the vertex. This can also be detected by using mechanics. Why? Well, when you have a gravity center, the purpose of the gravity center is to be simplifying the situation. Instead of considering the whole rod with balls and blah, 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 you can consider only one point, but you have to keep in mind the weight of the whole system. So this point you consider with the mass, which is the sum of the masses. You replace this big body by just one point, or if you want one ball, with mass sum of the masses. And if we apply this here, the gravity center of the segment will have mass m1 plus m2. And then what I observed was the hardest to explain to the kids was that actually the gravity center of the whole thing can be obtained by considering the gravity center of the gravity center and the third point. But once you convince them somehow, experiment, then you can immediately see what the ratio here is. Because you have M3, you have M1 plus M2, and by our property, we know that, well, let's give some names. We know that CG to GD is the same as M1 plus M2 to M3. Right? So that we immediately see that the medicenter will divide the medians in ratios 2 to 1. And this is given as a present. I mean, you do nothing, basically. Actually, this is not true. There is a conservation of difficulty. You know. The thing is that you put under the carpet the non-mathematical, the mathematical explanation by using some physical ones, hoping that the kids will understand the intuition behind what they see in the experiment. Yes.
I just wanted to say that you could, of course, use only mathematics if you use vectors. Then you can avoid all physics.
I'm heading there. Yes.
What about the confusion of the gravity center of the triangle and the gravity center of the three-point masses? Does that ever cause any trouble?
Ask you what?
You have weight. You have density in your triangle. The students ask about that.
Well, the thing is that my triangles, in my experiments, my triangles are made out of sticks. So you may, well, I had triangles like that here. So use...
Do you stay away from the solid lines?
Yes.
That was the question.
I want to be close to mathematics. But if you use cures, for example, you can easily make triangles and put some balls in. It's fun. It's fun. Unfortunately, on the experiment, the medicenter, the gravity center is never the place to, and it should be mathematically, but this is the experiment. This is actually. All right, so now what we can extract from here is the following rules, actually. First of all, every rigid body has a gravity center. Then if you split the rigid body into two bodies, then the gravity center of the whole thing, for example, like here, the gravity center of the whole thing is obtained by finding the gravity center of the system of 2 points with weights, the weight of this and the weight of that. For example, if you have the quadrilateral and you have 4 masses, and you want to find the gravity center of the 4 points, what you can do is you can split your quadrilateral to 2 segments. Then you know how to find the gravity center here because we have the rule. Find the gravity center here. Then you find the gravity center there. Then the gravity center of the whole system will be actually the gravity center of this system of 2 points only. No matter how you split the solid into 2 or more subsolids, you can find the gravity center by finding the gravity center of the system of gravity centers with the corresponding mass. So let's play with this. For example, why should these segments intersect in 1 point? Let's start with the lateral. So here we consider the mericenter, and we connect this mericenter to the 4th vertex. This is called the median in quadrilateral, if you know. And this mericenter is the gravity center of the triangle if the masses are equal. Right? Then the gravity center of the, well, this is the gravity center of the triangle. The gravity center of the quadrilateral will be obtained by using the 4th point and the gravity center of the 3 points. So that the gravity center of the quadrilateral will be somewhere here. Even we can find that point, because the mass here is 3 equal masses, and the mass here is 1. So that the ratio is 3 to 1. Right? And all the 4 medians will pass through this point. Okay, but you can find this gravity center by using segments. You can split the quadrilateral in different ways. For example, if you use the midpoint here and the midpoint there, the mass here will be 2, the mass there will be 2, the gravity center of the whole system will be belonging to this segment, and it will be divided into equal parts because nature is never wrong. So that you have plenty of segments which pass through 1 point, and you can see they pass through that point without computations. There is a degenerated picture of this one, which is also interesting. For example, if you consider a triangle and the point inside the triangle. And there are 3 triangles we want to play with, and what we do is we connect a vertex to the mericenter of the opposite triangle. Vertex to the mericenter of the opposite triangle. Vertex to the mericenter of the opposite triangle. These 3 segments pass through 1 point. And the reasoning is absolutely the same. It looks differently, and it may be weird, but the idea is the same. This point, the common point, is the gravity center of the system of 4 points. It's not a quadrilateral anymore, but we don't care. There are 4 points with masses, and we play with them, and we find the gravity center. Okay, so now one can use these ideas to proving some theorems in geometry, apart from the mericenter. the medians which intersect in one point. Here is one such example. When should I stop? 15? 9:50. So here is one other example which can be done by using gravity centers. The triangle, the incircle, the tangency points. And then we connect every tangency point to the opposite vertex. You know, they are concurrent. But, and this can be proved in many different ways. But the gravity center approach is just obvious. The thing is that we have to figure out what masses to put at the vertices so that this become the gravity center of the segment, that become the gravity center of this segment, and the third one becomes the gravity center of the third segment. And then you are done. And now to find those, well, the kids have to figure out that this segment is the same as that one, which is kind of standard. And by using the lengths of those segments, they can play a little bit and figure out the masses they have to put at the vertices. More generally, there is Cheva's theorem, which I know how to prove either by using vectors or by, which is almost the same, by using Mendeleev's theorem. But by using gravity centers, it's just obvious. What's the Cheva's theorem? We have a triangle ABC. We have points on the sides for which we know that there is a restriction. And then the conclusion is they are concurrent. Well, if we are to use the gravity center, we have to try at least to find masses to put at the vertices so that C1 is the gravity center of AB, A1 of BC, and B1 of AC. If we can do this, we are done. Because this common point has to be the gravity center of the triangle with those masses. And it's not very hard to figure out what masses to put. It's kind of. Of course, Cheva's theorem, well, there is limitation here coming from the real world. Namely that there are no negative masses, there are no zero masses. We don't care about that in mathematics, but the physicists, they are very cautious.
You can think
When dealing
of
with
charges.
this-
I mean,
Huh?
why not? I mean, what's wrong with negative or zero mass? I mean, zero mass is just nothing, and negative mass is like negative charge. What's
I
wrong
don't
with
know what physically means nothing.
that? No, I mean, think of charge instead of mass. And that will be exactly the same, like,
Yes, I have seen experiments with balloons.
yeah, like
Helium
in
balloons
a permanent, how do you call it, constant electric field or something. So that,
All right, but you remember that I have to explain this to the middle schoolers.
yeah.
Kind of. I know, I don't care about, I'm not a physicist. I don't care about the science of the masses because I know how to play with vectors. But if you want to build up intuition, what do? I have colleagues, teachers, who use balloons to explain the multiplication with positive and negative numbers. It was really funny. I'm not sure that the kids understand that better. I mean, if you give them by definition what is happening, then maybe it's easier. But the teachers, they don't think so. they want to have something which is going up and, I don't, it's not easy. If you have positive masses, everything around us has positive masses. You can easily set up an experiment with positive masses, but with zero or negatives, I don't know. And mathematics is a little bit much more flexible than the physics that we used here. For example, Cheva's theorem, well here, because of the positive masses, all the points had to be on the segments, right? But Cheva's theorem holds true even if some of the points are outside the segments, on the lines of the triangle. And there we need mathematics. And here we switch to, well, for middle and high school, we need mathematics. And here we switch to the mathematical model of what we can see here. And the mathematical model deals with vectors. To explain vectors to middle schoolers is a tough job. I've never been successful in that. For high schoolers, well, at least in our area, Florida, there are some kids who can understand what vector is. It needs time, but anyway, just to complete this presentation with the mathematical part, the model for what we see here is the following. First of all, we play with material points. A material point is just a point with a real number. It's an ordered pair, a point and a real number. Then we define systems of material points. Which is, well, finite system of material points. And then, being material, we want to define gravity center of this system of material points. And now the definition, it looks very elegant mathematically, and it's inspired by physical experiments, but it's not that straightforwardly coming from there. So the gravity center, it's a point with a mass, the sum of the masses, for which we have this relation, M1 GA1 plus and so on plus MN GAN is the zero vector. And this is exactly what is happening with the medicenter of the triangle. If you sum up the three vectors, you will see that no matter what masses you put there, I mean equal masses, the sum will be zero. Now this is a very nice definition, and by using this definition one shows that the gravity center always exists provided this M is not zero. I mean its existence is unique provided this M is not zero. And actually all the theory works if there is no subsystem of material points with sum of the masses zero. Because you have to be dividing from time to time by the sum of the masses, and you have to be careful. All right. Then it's very easy to show that, for example, if we have another system of points, with its gravity center, and you consider all the points together. So we now consider the system A1, M1, and so on, BS. I didn't mean it. Let's change S to something else. BP. I don't like BS. So BP and B prime. This will have a gravity center. With the corresponding mass, which will be M1 plus and so on plus MP prime. Now, how can we find this gravity center? Actually, this is the gravity center of the system of two material points only. GM, too many M's, and G prime, M prime. This, the gravity center of the whole system of points is actually the gravity center of the system of only 2 points. And by using the first, well, by using vectors, this property here is straightforward. Because if we have 2 points only, the property would be GA1 times M1 plus M2 GA2 has to be 0. Then another way to put that is this, right? So that we have this property there, and if we want to find the gravity center of a system of points, what we do is we split it into 2 subsystems. We find the gravity centers of the subsystems. Their segment contains the gravity center of the whole thing. Then you split it differently, find another segment. The intersection point of the 2 segments is where our gravity center is. And you can find all the ratios immediately by looking only at the masses without any computations. Now, this can be generalized further. For example, well, here I have used only the affine properties of the Euclidean space. Actually, there is no need to work in the plane, there is no need to work in the 3-dimensional space. Any dimension is okay, and we have used only linear things. We can use only the scalar product, the metric in the Euclidean space. And then the theory gets much deeper and much more closely related to mechanics. And very interesting theorems can be proved by using inertia, the moment of inertia system of points, and so on and so forth. But I don't think this is good for even high schools. I mean, this is for university. So again, what I wanted to do here is to show some way of building up intuition, actually quite an elementary way of building up intuition and giving means to the kids even detect theorems and also prove theorems. Yes?
When you're building up their physical intuition, do you actually have them measure things and balance things physically, or more just at the middle school, or do you actually just sort of show it on the board?
Standard beginning to answering such a question is, this is a very good question. Well, I used, for my experiments, I used Play-Doh. And very quickly, the kids begin using the Play-Doh as they should. For example, they make some pizzas and blah, blah, blah. So it's kind of tough for middle schoolers. But what I do is, in the beginning, everything is done by me. I mean, I show them, because some of them, the sad thing is that the middle schoolers, they have never seen anything physical. I mean, they have never seen experiments in their classrooms. They don't know what to do there. So you have to show them. You have to lead the process. And when you see they're already exhausted and their interest is somewhere else, then you suggest they do some pizzas and blah, blah with the Play-Doh. By the way, the same thing happened here the other day. I left the room for a while, and then when I returned, all the Play-Doh was not where it should be. But the toughest part is in the experiments. But I also know by my experience that the kids are absolutely fascinated by observing what is going on. You tell them this will happen, they don't believe you, and all of a sudden they see this is happening. So there is a way to attract their attention. And the most important thing for me is they have to know that the link between what we see around us, the real world, and mathematics is very short. And if you have the insight from what can never go wrong, you can't be wrong in mathematics. Yes?
Do you ever make a rigid triangle and put weights on it and try to balance on the pin or something like that?
This I try to do, but because I wanted to explain to the kids the meaning of the gravity center.
Yeah.
And the meaning of the gravity center is that, what I did for my son to see how it will work in the beginning, and then I gave up because it's too much of a work for an hour and a half circle. I made the triangle by using sticks and balls, and then suspending the vertices, I found the points of intersection of the vertical lines with the opposite sides. And then I use string to connect the vertex and that. And I was amazed to realize that actually the three strings, they met in one point. And when you use glue so that you fix the strings, the super glue, whatever, and then when you get the triangle at this point of intersection, you see that no matter how you put it, it's in equilibrium. And that's the idea of the gravity center. If you get a little bit off it, the triangle will always get to a position so that the gravity center is strictly below your fingers. It's amazing. I was amazed. I wanted to do it but it needs time. Or you have to be very good in this, immediately. Or you have to prepare it at home and just show them. What I did here was, on a board, I fixed the 3 points, and then I used strings connected to what was to be the gravity center eventually, and put some weights. Well, and then this point, when it is in equilibrium, it has to be the gravity center of the system of 3 points. For example, if the masses are equal, this has to be the main center of the triangle.
But why? I mean, probably has to. I mean, it's a different law. It's not the same.
Why? Because the gravity force here is the same as the corresponding one. If the weights are the same,
yeah, that's what I'm saying. I mean, it seems to me like they should make angles of 120 here. Should they? If all 3 masses are the same, then it should be in such a position that all 3 angles are the same. Otherwise, they don't add up to 0.
No, the pivot points are different. Pivot points are different places.
Yeah, that's what I'm saying. That's what I'm saying. I mean, so basically you got 3 vectors of the same length, and you want to add them up to 0. And in order for them to add up to 0, they should make angles of 120. It will be all different points. Or am I wrong? Yeah, it's altogether different. I mean, only for equilateral it will be the same.
I think he's right.
yes, okay. So this was wrong.
But if you just have 3 poles, then
No, I mean, it should be a point that makes all triangles the same. Only then they will add up.
Well, I was not able to make this point the main center. Maybe
No,
this
sure
is
not.
why.
I mean, except for equilateral.
Yes, okay. Yeah, you're right.
But did you measure the angles? I mean, they're supposed to be, all 3 angles supposed to be 120, if I'm right. I mean,
All the triangles should be what?
no. The 3 angles made by those 3 strings from that point of where they connect,
120, yes.
yeah, they should be 120, yes.
I didn't measure, but they have to be.
Okay.
So that, thank you.